Hello students, welcome to our next session in design and analysis of algorithm. So hope you are all doing good. So today now we are going to start a new technique called as a greedy technique, or it's also called as greedy approach. So already in our previous session, so we have discussed a lot of algorithmic techniques, right? So we started with brute force technique. So then we discussed a divide and conquer technique. So then we have discussed decrease and conquer technique. So all these techniques are different ways in which you are going to solve the particular problems, and we have taken quite a few examples in each technique, and we have seen how to design and even the practical implementation of all those techniques also. So today now we are going to start with another new technique which is called as a greedy technique, or it's also called as a greedy approach. Now what does this particular greedy technique tells us? Now this is a technique, now this is used for designing optimization problems. So now you have to understand what is an optimization problem. Now optimization problems are those type of problems now where we have to find either the maximization or minimization. That is the major goal for us for any function when you are going to consider, or any problem you are going to consider. Major goal will be either to maximize or to minimize, right? So such a type of a problem we call it as an optimization problem, and all these type of optimization problems will have some set of constraints, right? So now they will be having some set of constraints. Now you are supposed to satisfy you are supposed to satisfy those type of constraints. So now what do you mean by a constraint? Or say for example, now if you take a travel salesman problem. Now we have seen travel salesman problem, right? Now travel salesman problem is one example now which comes under the optimization problem. Now what is the major goal here? Now we have to find the minimum distance. That means a salesman supposed to travel various cities, like say for example the salesman has to travel from city A, B, C, D, E. So he can go in any direction, or we can say any cities he can visit, but ultimately he has to come back to A. So now here now you have to find a particular path in which, or we can say the path should be very minimum. That is, the total distance traveled by this particular salesman should be very small. And what is the constraint here? So now what is our minimization in this example? The minimization is the total distance he is going to travel should be very less. And this particular problem, or TSP, or travel salesman problem, is subjected to constraint. Subjected to constraint means now he can visit the cities only once, right? Now he cannot visit a city two times. Now that is our, what we say, the constraint. So any type of optimization problem so now is subjected to the constraint. Now so now we have optimization problems, right? Now greedy strategy, now it always tries to find the best solution for each of the sub problem. So when we are telling optimization problem, you have to optimize. Say for example, now when you consider our travel salesman problem, now in your travel salesman problem, now you have got three solutions, let us say, in front of us. Now these three solutions, or three paths which is there in front of us, now it has satisfied all the constraints, right? So now by you are starting from city A and you are ending up with city A, and you have traveled all the city exactly once, so constraint is satisfied. So you got three different paths. Now these three paths we call it as feasible solutions. So these are called as a feasible solution. So why we call it as feasible solution? Because all these three paths has satisfied the constraints. Just the constraint. Till now we don't know which is the minimum, which path is taking the minimum distance for us. So only thing is that now all these solutions, or all these paths what we got, now it satisfies the given constraint for us. Since it is satisfies the given constraint, now we call them as a feasible solution. Now out of these feasible solution, you are going to pick one path which is minimum, so whose distance is very small, then that becomes an optimal solution. right? Now when you are talking of optimization problem, now we have two types of solution. One is feasible solution, the one is optimal solution. So what is the difference between the feasible and optimal solution? Now feasible solutions are those solutions which satisfies the constraints. Clear? Now optimal solution is the best solution out of the feasible solution. Now if you have feasible solution, if you have 5 feasible solution, out of these 5 different paths in which you are going to visit, the salesman is going to visit. Now out of these 5 feasible solution, which is the best one? Now that is called as optimal solution. So now we see that now the greedy strategy now always tries to find the best solution for each of the sub problem, now with a hope that the result will be good for our actual problem. Now here what happens is that now you are having a particular problem or a goal, right? So now you start from an initial state. Now step by step you try to go. So you go to the next step. So from this particular solution or a starting state, now you go to the next solution. Now what it happens here is that in greedy approach, now step by step you are going nearer to your solutions. So when you are at this stage, now in front of you, now there might be 3 feasible solutions, right? There may be 3 feasible solutions. Now out of these 3, you are going to select one best. So at this moment of time, you are selecting this as our best solution. From here, now you try to go to the goal. So the greedy approach, it suggests us to construct a solution for the subproblem through sequence of steps, right? And each steps expands a partially obtained solution. So now we are going to have a partially obtained solution until we reach the final state. Now when we are trying to use this greedy approach, now these are the 3 important words which we generally use in this technique. The first one is called as feasible, right? Now we have already discussed what is what do you mean by a feasible solution. So feasible means what? Satisfying the constraints of the problem. So now for your particular problem, now if you have got some constraints, now what all that constraints? Now if you satisfy all the constraints of your problem, so then we say that so your particular solution is a feasible solution. Then locally optimal. Now locally optimal means what? Now understand it carefully. So locally optimal means it has the best local choice among all the feasible solutions, right? So local choice among all the feasible solution. Now if you look here, now from this point to reach your goal, now you are going in some direction, right? Now in front of you, you got 3 feasible solution. So there is one path going from this side like this, it reaches the goal. So there may be one path which reaches from here, and there may be another path which goes in this direction, and from here also you can try to go and reach the goal. So in front of you, you have 3 paths are available for us. So that means you have 3 feasible solution for us. Now out of these 3, which is good, right? Which is good locally. That means so at this moment of time, you may find that now this path is good for you. This may give you the smallest distance towards this goal, but you don't know what is going to happen in future, right? In further when you go, you don't know, there might be some road may be cut, or you can say there might be a traffic jam, you don't know in future. But at this moment of time, right, at this moment of time, that's what we say locally. So at that moment of time, you find that path, so going in this direction is good for you, so we call it as local optimal. So the third important definition is irrevocable. Now irrevocable means once a choice is made, now it cannot be changed, right? So once you make a choice, you cannot change it. Like say for example, now you are going to take the game of chess. Now when you are playing chess, now once you make a move in a chess, you cannot go back, right? You cannot go back because the rules is like that. So when you are going to play a chess, the rules is such that once you make a move, that is one of the rules, once you make a move, you cannot go back. So we call it as irrevocable, right? These are the some important terms which we generally use. Now what we are going to do is that now in greedy approach, now each step we look at an optimal solution. right? So you have so many feasible solution. From feasible, which is the best one, that is the optimal solution we try to look, and greedy technique yields the best solution for many of our problem. So for various problems, now greedy technique gives us the good solution for us, but there is a drawback also. So there is a drawback in applying greedy technique also. What is that? Now, so you, without aiming at your final solution or your goal, if this is your goal, without aiming at your goal, you are at this particular place, right? From here, excuse me. Now you are going to say that this is the local. So local optima, you are going to obtain local optima. So now you find that this is good at this moment of time, but you don't know what is going to happen. That is the major drawback, which you are going to get in the this particular, you can say, greedy technique. Now let us take an example, right? So some simple way to understand. Now say how the greedy is going to work. Suppose you have got some set of coins. Now you are having some set of coins, like say you have got 5 1 rupee coin and 3 5 rupee coin, 2 10 rupee coin, and 25 rupees 2 coins. Of course, in India we don't have 25 rupees coin. Let us just assume. Okay, so we have 2 coins. Now you are supposed to give change for 43 paise. Now you are supposed to give change for 43 paise. Now this is what it is there with you. Now how do you start giving change to any person or a customer? So what we do, the greedy technique says that first we will take the highest possible value, which is less than or equal to 43. Now you are going to give the change for 43. So now in front of you, so when you have got so many coins, now to give change for 43 paise, you won't start giving from 1 rupee coin, right? Now what we do, so we take the highest one. That means now we try to take 25, because 25 is just less than 43. So you select 25 paise coin, right? Another 25 paise coin, if you select, you will get 40, you will get 50 paise, but you have to give 43. So next what you do, next you go to the next largest, next you take 10 paise coin. So 25 plus 10, now you will get 35, right? Now then can you again take another 10, because another 10 if you take, it becomes 45. No, so you will take 5, right? So like this, if you look into the solution, so you take 25 paise, 10 paise, 5 paise, and 3 1 paise. When you find the total, now this total becomes 43 paise. So now we won't start from the 1, so we start from the 25. So that is what the greedy technique is going to tell us, right? So now this we will try to take some examples, and we'll try to see now how the greedy technique is being used in order to solve the problem. Now the first problem what we are going to consider here is finding the minimum spanning tree. Right? Now the problem is, now you are supposed to find a minimum spanning tree. Now here, now we have got 2 algorithms are there, right? Here we are going to have 2 algorithms. So one is called as the Prim's algorithm, the second one is called as the Kruskal's algorithm, right? So now before going into the algorithm, now you should understand what do you mean by a minimum spanning tree, right? What is a minimum spanning tree? Now how are we going to define a minimum spanning tree? So now we define as follows: a connected acyclic subgraph, right? A connected, so the graph should be connected. The second point, acyclic means now it should not have any cycle. So you know, we have seen what is the definition of an acyclic. So a connected acyclic subgraph containing all vertices of a connected graph, right? Containing all the vertices. Now say for example, now you are given a graph, you know that graph G. So you are given a graph G. So now graph consists of what? Set of all vertices and set of all edges, capital E and capital V. So where capital V is set of all vertices and E is set of all edges. Now you are given a graph. So now how do you define a spanning tree? Now spanning tree means what? It is a subgraph. First thing, it is a subgraph of this graph, right? And it is connected, it is acyclic. So a connected acyclic subgraph containing all vertices of the graph. So now if you consider a spanning tree, now let us take a subgraph T. Now this, when you are when you are saying that this is a subgraph, now this tree also has some set of vertices, right? Let us call it as v dash, and some set of edges, let us call it as e dash, right? Now what it says, what the definition of a spanning tree says is that, now this is a tree, that means it is a subgraph, right? It is a subgraph of this. Now this, all the vertices in this tree are connected acyclic. There should not be any cycle, because if there is a cycle, it becomes a graph, right? It becomes a graph, but this is a tree. So the definition says spanning tree. So it should be acyclic, subgraph, connected, and another, what is the another constraint? The another constraint is this v. So how many vertices was there in our graph? You should have same number of vertices in our tree also, right? Containing all vertices of a connected graph is called as a spanning tree. Now this is our definition of a spanning tree. So how are you going to define your spanning tree? So a spanning tree is nothing but a connected acyclic subgraph, so which contains all the vertices of the given graph. So then we call it as a spanning tree. Now our goal is to find the minimum spanning tree. Now we are supposed to find the minimum spanning tree. Now next we'll come to the what do you mean by minimum spanning tree. So now all these edges of our graphs are being labeled. So we are going to label all the edges, right? Now all the edges are been labeled. Now when it is been labeled, we can assume that some distance has been given. So now when you are going to count all the distance, now so which tree is giving you the minimum value, we call it as a minimum spanning tree. We call it as a minimum spanning tree. Now let us take an example and we'll see. Now let us say this is our graph, right? I think you can see here. Now it is a graph. Now it consists of 4 vertices A, B, C, D and E, and all the edges are been weighted. So we can call this as a weighted graph, right? It is a weighted, and you can see all edges are connected. That means all vertices, if you start from A, you can reach to B, or you can reach to C, you can reach to D, right? Or you can reach to E, any path. So that means it is connected, right? And weighted. Why we call it as weighted? Because some weights are given. From from vertex A to B, the cost is 1. From B to E, cost is 7. Like this, all weights are been given. So now you have got a connected weighted graph. Now this is a graph G. Now we have to construct the spanning tree for this graph. Right, you have to draw a spanning tree. Now what we told, one of the important constraint, now the spanning tree also should have all vertices what the graph is having. So now what all the vertices graph is having? So let us say graph has got A, now B, now C, this is E, and this is D, right? So it has got 5 vertices. You are having 5 vertices. Now the spanning tree should contains all vertices of our graph. Now it should be connected, right? Connected. It should be connected. So now so from B to E we connect, and let us say that from here to here it is connected. From here to here it is connected, and from here to here it is connected. Now if you say that this is vertex A, this is B, right? So this is your vertex E, now this is your vertex C, and this is your vertex D. Now A, B, C, D, E. So 5 vertex are connected. Now you see, is this a subgraph? Yes. One constant we have satisfied, it is a subgraph. Is it connected? Yes, it is connected. Do you have any cycles here? There is no cycle here, right? Suppose say that if you connect from A to B with one edge, so you get a cycle, but spanning tree does not has a cycle, so you don't have any cycle here. So all constraints are been satisfied, right? So now from A to C it is connected. So now you take down what is the weight from A to C edge. Weight is 4, right? From B to E the weight is 7, and from C to E weight given is 5, and here the weight is 3. Now you will add all these weights. So how much you are going to get? So 7 plus 3, 10, 15, 14. So the total weight you got or total cost you got is 14 for this spanning tree. Now we are going for minimum spanning tree. Now is this only one spanning tree can you construct? No. Right? Now we can try to construct another tree. Now here you can see, now there is another example. Now this is also a spanning tree. Now why it is a spanning tree? Go with the definition of a spanning tree. Now it is connected, right? Yes, it is connected. Acyclic, no cycles are there, and all vertices. Now this tree is a subgraph of this graph. Now you see graph has got 5 vertices. Now tree is also having 5 vertices. So it is a spanning tree. We accept that now this is a spanning tree. Now take all the cost which of these edges and find the total cost. Now total cost you are going to get 13. Now this tree, this was a spanning tree. What is the cost you got? 14. Now you got a tree, cost is 13. We will draw another spanning tree. Now this is another spanning tree. So from A to C it is connected, B to E it is connected, C to E it is connected. Right? So and from here to here it is connected. I think this is 19. We got the same spanning tree. Correct? Now what we can do is let us delete this edge. Right? Now if you delete that edge, now it is a disconnected. Now you can see that it is a disconnected. But spanning tree means what? It should be connected. Now we will connect this here. We will connect from A to B. What is the cost from A to B? A to B cost is 1. Right? Now we will find the total. So 10, 15, 16. Now the total cost of this spanning tree is 60. Right? Now this is our one spanning tree. This is the second spanning tree. What was the total cost we got of this spanning tree? 13. Now we have another spanning tree. Now when you find the total, you get 19. Like this, we can draw various other spanning tree also. Clear? So now, if you count these total, which spanning tree gives you the minimum? Right? Now here T1, this is having 13, so the cost is very less, so we consider this as the minimum spanning tree. So you won't get any other, you cannot construct any other spanning tree whose total cost is less than 13. So now this technique, now we call it as exhaustive search technique. So exhaustive search technique means what? You keep on drawing. First you draw this tree, then you draw this tree, then you draw this tree. Like this you construct all the trees. After constructing all the trees, that means after constructing all spanning tree, now you try to find its total. Okay, so the first spanning tree's total is 16, the second spanning tree total is 13, then 19, then so and so, so and so. After finding all the total of all spanning tree, then you will check which is minimum. Now that method is called as exhaustive search. Right? So first what does it says? First find all possible spanning tree, then select the minimum among these. And you know that if you keep on doing this, now it consumes lot of time for us. So it consumes lot of time for us. So to avoid that, now we are going to use some of the algorithms. Right? The first one is called as the Prim's algorithm. Right? Now Prim's gave us an algorithm through which you can find straight away a minimum spanning tree. So that means now input you are going to give as a graph. Right? So you are having a graph as an input. Later we will discuss this in our lab session also, how to implement this, right? How to find a minimum spanning tree. So now let us go and look into how to solve by using Prim's algorithm. Now this algorithm, it constructs the minimum spanning tree through a sequence of expanding subtrees. Right? Now you are going to find the minimum spanning tree by expanding, by sequence of steps. That means initially you will be having an empty tree. So then you start with an initial vertex, then step by step you are going to construct the tree. So step by step, finally you construct one spanning tree, and that spanning tree, it will be the minimum. So the initial subtree is taken as any arbitrary vertex. Now you can start with any vertex, because we know that spanning tree should have compulsory all vertices of our given graph. Right? If a graph has got 3 vertex, spanning tree also should have 3 vertex only. Because if one vertex is less, it won't satisfy the definition of our spanning tree. So the initial, so you start with any arbitrary vertex. So once you start with one arbitrary vertex, then what we do among the other vertices of the graph. Right? So then the remaining vertices of the graph, now you are going to find the nearest vertex to the existing vertex. Like say for example, you start with vertex A. Now if you start with vertex A, so now still 4 are remaining. Right? Still 4 vertex are remaining. Now in this 4 vertex, which is very close to A, now we select that. That's what it says. So among the other vertices of the graph, the nearest vertex to the existing vertex of the tree is found, and it is attached to the tree. So initially you are having a graph, right? You are given a graph. So then you take a null set, we call it as a spanning tree T. You start with an initial vertex, right? So let us say here one graph is there. So when you try to solve an example, now it will be more clear for us, right? So let us take that this is our graph. Some graph is there. You start with any one vertex. So from this vertex, if you assume this is your starting vertex, now there are 2 adjacent vertices here, this one and this one, which is very close to that. You include that into you bring that into your tree. Right? So second step. First step with only one vertex, next you have included this, you have joined. Next you take another step. In another step, from here, now which is nearer, you will identify and you will add that. So you keep on step by step, you keep on going. So the procedure is continued till all vertices are included in the tree. Now finally when you see, you have to see that all these vertices in graph, how many vertices graph has, all vertices should come to our tree. Now this is the procedure. So what we are telling here is that if capital V is the set of all vertices of a graph, then capital V subscript T will be the if capital V T is nothing but the vertices in our spanning tree. That's why subscript T is written. And Vt is that of minimum spanning tree, right? Our minimum spanning tree vertices, we represent it by capital V small t. Just capital V means these are the vertices of the given graph. So now what we are going to do is, so now this is the procedure. That is the algorithm. Step 1, what we do is that now we move U star. Now U star is one particular vertex when you take, right? So it's an edge. So U star from this set V minus Vt. So that means you take one vertex. Sorry, U star is one particular vertex. Now you move this vertex U star from the set V minus Vt. That means the difference, right? So totally, if you have got 5, so 5 vertex in graph, then our spanning tree vertex at the first step is null set, because there is no. Then you add one vertex into this, right? Then leftover is 4 vertex will be there. Now out of this 4, you take one vertex U star from this set, and we move that to Vt. You are going to move it to Vt. And for each remaining vertex U, and for remaining vertex U in V minus Vt, that is connected to U star, right? So that vertex U which is connected to U star by a shortest edge. You have to find the shortest, right? Right, because our goal is minimum spanning tree, we have to get minimum. So which edge is very very nearer to that? Now you consider that edge is, right? If you consider any vertex U, and if that is connected to U star by a shortest edge, then U's current distance label is updated. Now you update that particular label and you add that U star into the set of all vertices of your spanning tree. Now this is the procedure how we are going to find the minimum spanning tree. Now let us take an example and we'll try to understand how we are going to calculate. So now this is a given graph for us, right? So we have given a graph. Now how many vertices are there? 1, 2, 3, 4, 5, 6, 7. So there are totally 7 vertices are given in our graph. Now it is a connected graph. It is a weighted graph, right? So now we start working with the Prim's algorithm. Now before you start, now we are going to mark 2 columns here. The first is called as the tree vertices and another set is called as remaining vertices. Now we start with the tree vertices. Now let us assume that you are going to start with the vertex A. So this is your starting vertex. So you are going to start with the vertex A. And initially, so you are taking 2 subscript here or 2 values you are going to write. Now we will come to know what are the 2 values. Now this is the initial. So now if you consider A in your set of all vertices of your spanning tree, right? So now this is the spanning tree vertices. Clear? So now when you consider your graph G, right, if you consider your graph G, now graph G has got set of all vertices, capital V and capital E. Clear? This is how you are going to define a graph. Now what the set of all vertices are there in your graph? Now if you consider all the vertices in your graph, now how many vertices are there? Now you have got A, vertex A, B, C, A, B, C, etc. up to A, B, C, D, E, F and G. Right? Now these are all the given vertices in your given graph. So now at the starting phase or the first step, you start with an arbitrary vertex A. Now you add this A to your VT. Now initially the set of all vertices in your spanning tree, what will be initially the set of all vertices in your spanning tree? It will be a null set. No vertices are there. Now first step, what you do in this set of all vertices, you are going to add vertex A. You are going to start with vertex A. So you add this. So this left side indicates the tree vertices. Now when you add A from this vertices, if you add A, now what are the remaining vertices? Now the remaining vertices are B, C, D, E, F and G. Right? Now right side we will write down the remaining vertices. Right? Now you are starting from A. Clear? So you are starting from this A. So now what are the remaining vertices? Now remaining vertices are there. Now in this right side, now we will start with B. So we will write B. So now the first subscript is, now you see that from A, because you are hit here, from A can you go to B? Can you go to B? So from A to B, is there any edge? So from A to B, yes, we have an edge. So we will write A comma. That means from A to B there is an edge. What is the cost of this edge? The cost of this edge is 2. So I will write comma 2. Clear? This is the remaining vertices. You have added A now. You have added A to the left side. That means in your spanning tree. So now the first step, your spanning tree has got vertex A. So now this is your vertex A. This is your vertex A. Now we will look into the remaining vertices, and from this remaining vertices, which vertex is very nearer to A you have to find. That is what minimum, right? So now B is completed. Now B is completed, we will go to D. So the next vertex you will take D. Now bracket. Now is there an edge from A to D? You will see, is there any edge from A to D? Yes. So we will write it here. A. So that means A to D you have an edge. What is the cost from A to D? Cost is 3. So A comma 3. So we will write D of A comma 3. Now you can see here we have written D of A comma 3. So now, right? Now B over, D over, now we will come to C. Right? So from D you have C and E. Sorry, from B. So from A you went to B. Now from B, so you can see that you have got B, D, right? So D is over. Now we will go to let any vertex. You can take any vertex because still what are the vertices remaining? C, D is there, E, F and G. So we'll take C. We'll take C. Now from A, is there any edge to C directly? You don't have. Right? From A, you don't have any edge to C. So since you cannot, C is not visible from A. So if you are standing here, you cannot see C because there is no direct edge. You have to go via B. Correct? So what we say, we write C dash. So that means it is not visible at that moment of time. So from A directly you don't go, you cannot go to A. So what is its distance, that also you don't know right now. So we will mark it as infinity. Clear? Now A is over, B is over, C is over, D is over. Now we will go to vertex E. Now these are all the remaining vertices. See, after adding A to the set of all 3 vertices, how many remaining vertices are there? One by one we will check. So now you go to E. Now you check that from A, can you go directly to E? So you cannot go directly to E to A. So here also we will write dash, and what is the distance? Since there is no direct edge, we will write it as infinity. Right? So next remaining vertex will take F. So now you see from your graph, from A can you go to F? You don't have direct edge. So we will say F also dash comma infinity. And the last remaining, so edge is G. So we will write for vertex G. Now from G you don't have direct edge from A, so this is also dash comma infinity. Right? You added A. In the first step you added A into the set of all spanning tree vertices, and remaining vertices you found the distance. Right. Now when you have marked all these here, now you find which is the minimum. Now if you look here, from A you can go to B, cost is 2. From A you can go to D, the cost is 3. Whereas other things are all dash. That means if you are at this particular vertex, now you can see that there are only 2 vertex which are adjacent to this. One is B, other one is D. Now from A to B, cost is 2, A to D, cost is 3. So which is minimum? This is minimum. So from A to B with this cost of 2 is minimum. So you underline this particular thing minimum. So you found that now this is the minimum distance. So from A to B if you go, it is going to give you the minimum cost. So now you add this to the left hand side. So now what we do, initially you started with A. So now what you have found, from A you can go to B, from A you can go to B with a cost of 2, So now we will draw the spanning tree. Next step, so what we are going, so you go to vertex B, from A to B you have connected with an edge 2, with an edge that is cost as 2, right? So now A is over, B is over, node B is over, or vertex B is over. So now in your set of all vertices of your tree, now 2 vertices are there. See, totally how many vertices are there in the graph? 1, 2, 3, 4, 5, 6, 7. Sorry, there are totally 7 vertices are there. Now 2 is there in your set of all vertices. Now so still remaining is 5. Now identify what all the 5. Right? Now we'll start with D. Now D. Now from A you can go to D. From A you can go to D. Yes, because it was there. So we will write it as it is. So D, from A to D, cost is 3. Right? So the next node is E. Now to E, now from A, can you come to E? No. Right? So we will start writing. So let us say that this is how we do. So now the another remaining vertex is E. Right? Now E. Now from A you check, because A is also already present in set of all Prim's algorithm, that is in the spanning tree vertex. So from A to E, is there any direct path? No. You don't have any direct path. Now check with B. From B, is there any path to E? Yes, you have got a path from B to E. So from B you can come to E. you can come to E. What is the cost from B to E? It is 1. So you write on that 1. Right? So now D is over, E is over. Now still remaining D is over, E is over, A and B is already present here. Now we will take C. Node vertex C. Now to C, from A you don't have any edge. Now C from B, yes, from B to C you can go. There is an edge from B to C. So we will write B comma, and what is that cost? The cost is 9. So I will write 9. So next we will go for another remaining vertex F. Now from A to F you don't have any edge, whereas from B to F you have an edge. So from B comma, that means from B to F there is an edge and the cost is 4. So we will write B comma 4. And the last remaining node is G. And similarly you will see that for G, from A you don't have direct edge to G, from B also you don't have direct edge, so we will say dash infinity. Dash infinity. This is our second step, right? Actually it is the third step. First step is empty set. So now when you have written this, find the minimum value. So the second part, now you can see here 3 is there, 1 is there, 9 is there, 4 is there, infinity is there. Which is minimum here? This one. Cost is 1 here, right? This cost is minimum. You add that to the left side, that means under 3 vertices. Now what you are adding under 3 vertices? You are adding from B to E. If you go, the cost is 1. Again you draw another tree. See, in the examination you have to keep on drawing. So the next step what you are going, you have already these two, right? So next step, what you, from B to E. So from B to, you take this as an edge E, right? So from B to E you are drawing a graph. From B to E, the cost is 1. This should be another graph, right? You have to, each step you have to keep on drawing a subtree in your examination. Clear? So now how many vertices came here in our tree? 3 vertices came, totally 7 are there, still 4 is remaining, right? Now we will go to the next step. Now what are the remaining vertices? Now this came this side, right? Now the remaining still is D. Now we will consider the node D here, or vertex D. Now from D to vertex D, now you can see from A you can go to D, right? What is the cost? Cost is 3. From B, is there any edge? No. What about E? From E there is an edge to D. Now you listen carefully here, observe carefully here. Now from E there is an edge to D, but what is the cost? 5. But from A also there is an edge to D, right? From A also there is an edge to D. What is the cost? 3 is the cost. So now what is minimum here? This itself 3 is minimum. So we don't update, or we don't update it to 5. We will just say to D we can come from A. From A to D the cost of 3 is still less for us. So we don't select that one. We don't select this one. Right? Now we will go to the next vertex, remaining vertex, that is C. Now you start from here. What all is there in your left hand side? So now this is your node C, vertex C. From A, is there any edge? Direct edge? No. What about from B? Yes, you are having an edge. From B to C the cost is 9. Now what about E? From E do you have an edge? No. Right? Suppose if there was an edge from E to C also, right? Now you have an edge from B to C also. At that time, which is minimum, that will come here. You have to update. But anyhow, right now from E also you don't have. So now to C, only one is from B only you can connect. So we will say B. So from B to C, what is the cost? The cost is 9. Right? So now we will go to the next remaining vertex, that is F. Right? So now F. So for this vertex F, now from A you don't have edge, from B you are having, from E also you don't have edge. So what is the edge which is connecting to F? That is from B. From B you can go to F, and the cost is 4. Right? Now here count how many vertices we have included. 1, 2, 3. This side 3. That means 6. Still 1 is left. Totally 7 vertices should be there. So 1 is left. What is that? G. So we will take that remaining vertex G. Right? No. For G, from A you don't have an edge. From B you don't have an edge. Now from E you are having an edge. Right? Now from E there is an edge to G with a cost of 4. So this is E comma, what is the cost? 4. E comma 4. Right? Now total 7 vertices are completed. Now in this you find which is the minimum cost. Now here 3 is there, 9, 4 and 4. So we will take 3 as the minimum. Clear? Now suppose say that if you are working with some problem, sir, what happens if you get 2, like say here if there is another node, if this is also value is 3. So now if you get 2 times 3, or if the 2 vertices are having same, so then which one to select? Then arbitrarily you can select any vertex. Right? There is no rule. You can select any vertex arbitrarily. So now 3 is the minimum. So this is the minimum. So what we are doing in the next step, now you add this to the left hand side. So now here in the left hand side we will add this A to D edge. You are going to add an edge from A to D with the cost is 3. We add from A to D. So now from A to D you are going to add. So now this is your node D. So now by this time, so how many trees you have to draw? 1, 2, 3, 4. So like this, here I am just drawing this in same one, but you have to draw 4 times subgraph, right? Stepwise. Once you finish this particular step, by the next of this there should be one small subtree. After this step there should be a subtree with A and B as vertices. After step 3 there should be a subtree which has 3 vertex A, B and E. Here A, B, D, E. So like this, now you have to, each step you are supposed to draw the tree. So now you have added D into this. So you have added D here. So now again the next step we will look remaining vertices. Now you see 1, 2, 3, 4. So 4 vertex are there here out of total 7. So left still remaining vertices are 3. So what are that vertex? So we will write one by one. So we will start with C. Now C is still remaining, right? C is not present here. So it will be in the right side. Now from A, we start from first. From A, is there any edge directly to C? No. From B, yes, you are having an edge. Cost is 9. What about from E? From E you don't have. And what about from D? From D also you don't have. So only edge to C is from B, right? And the cost is 9. So we will write B comma 9. We are going to write B comma 9. So the next remaining vertex is F. Next is F. So from A you don't have edge to F. From B, yes, we are having an edge which is cost is 4. Now from E you don't have. From D also you don't have. So to F you have got an edge from B and its cost is 4. And the last vertex is G. Right? So from A you don't have edge to G, from B you don't have, from E you are having an edge to G with the cost is 4, and from D you have an edge to G. Now you see here, from E also you have an edge to G, from D also you have an edge to G. Now out of this, which is minimum, 4 or 7? 4. So you add this. So here what we say, from E to G, you go from E to G with a cost of 4. Now this is very very important. You have to remember here, because you see here, now when you are considering this G, right? So there are two edges. One is from D and the other one is from E. But if you go from D to G, cost is 7. From E to G, cost is 4. Which is minimum? You add that. So this step, now you got 9, 4 and 4. Right? So now there are two nodes. There are two values where you have got 4. So what we do, arbitrarily we will select the first one as the minimum and you add this to this side. So in our spanning tree, so we will add F from B comma 4. F B comma 4. It comes here. Again you have to draw your spanning tree. So F, this is your vertex F. So which edge you are adding? From B to F, and the cost is 4. The cost is 4. Clear? So now still how many is remaining? So 1, 2, 3, 4, 5 is completed. Still 2 vertex are remaining with us. Now we will, in the next step, we will write down those 2 vertices. Right? 2 or 3. Clear? So we will start the remaining vertices. So it is C. Now from C, no, from A to C you don't have any edge. From B to C, yes, from B to C you have an edge and the cost is 9. Now what about from E? You don't have. From D you don't have. From F you are having an edge to C. Now there are two things. One, from B to C you have an edge, cost is 9. Another is from F to C you have an edge, cost is 3. Which one you are going to take? So you are going to take, that is F. From F to 9. Right? Sorry, from F to C. What is the cost? The cost is 3. We will leave this, we will drop this B to C, because from B to C cost is 9, whereas from F to C the cost is 3. F is already present here, right? So we will say from F to C cost is 9. So we will write this one, right? So you just drop this here. So next one is node G, right? So here 1, 2, 3, 4, 5, 6, 7. Totally 7 vertices are there. Now you take your node G and you see is there any edges directly comparing one by one from here. From A there is no edge. From B direct edge is not there to G. From E you are having an edge, right? See, from E you have an edge. What about D? From D also to G you have an edge, right? What about F? From F also you have an edge to G. So now to G, so you are 3 edges. From F you are getting one edge, from E you are getting, from D you are getting. Out of these 3, which is minimum? 4 is the minimum, that is from E to G. So we will write down E to G. What is the cost? Cost is 4. Right? So now we will have two things, two values. One is from E to G, cost is 4. Other one is from F to C, cost is 3. Now out of this, which is minimum? Now this one is minimum, right? So this you strike it off. This is not okay, because that cost is more. So now we add this here. So now you add C from F to C in your spanning tree. So F comma 3. Now you add F to this spanning tree. Now you are left with only one edge, that is G, right? So G. So now if you consider this G, now again if you do, so to G 3 edges are coming. One is from D, one is from E and one is from F. Which is minimum? That is from E. So you will say E to G with a cost of 4. So now only one vertex is left. Now you add that also to this tree. So add that also to your tree, right? So now you get a null set here. So you can stop your algorithm. So you are going to add G, that is from E to G with a cost of 4. right? So now each stepwise, now when you try to draw this tree like this, right? Now finally, now this is your this spanning tree you are going to get. So what was the first node you added? You started with node A. So you started with node A, right? This was the initial starting node. So next step, what you went from A to B, you draw. From A to B, cost is 2. So from A to B, you connected from A to B, the cost is 2. Next step, another. So in this step, only this thing you have to draw, whatever is marked in green color, highlighted in green color, that you have to draw. That means after your second step, now you should have, in the examination you have to draw like this. So after the second step, you have to draw one subtree, which is that from A to B with a cost of 2, right? A to B. Next, B to E with a cost of 1. So next, what you are going to do, next step, again you have to draw the same thing what you have drawn in the previous step. That means from A to B, cost is 2. Then from B to E, from B to vertex E, cost is 1. You have to connect like this. Next step, so from B to E. So then B to E is over. Next, A to D, cost is 3. So you have to draw from A to D with a cost as 3. Again you have to draw in next third step, again you should draw another graph. Like this, stepwise you have to draw to get more the complete marks in your examination. So like this, step by step when you draw, now you get this as a spanning tree. Now you find the total. You find the total of all the cost, right? So what is the total you are going to get? 3 plus 2, 5, right? 6, 3 plus 2, 5, 6, 10, 14, 17. So what is the total minimum cost you are going to get? 17. So this is your final answer. This is the minimum spanning tree, right? So this is your minimum spanning tree. So today's class, now we have started with, so we'll try to wind up today's session. So we started with the greedy technique. What is the greedy technique? And we defined what is the spanning tree and minimum spanning tree, and we have taken the first algorithm called as the Prim's algorithm. So right now we have not seen the algorithm, now we have just seen the method, Prim's method, and we have taken one example and we have seen how we are going to solve this particular example. So in the next session we will take another example. So because first you try to practice whatever the example today you have seen, so you practice that particular example. So in the next session we will take up another example on Prim's algorithm and we will try to solve it by using the same method, that is the Prim's method, and we will look into the algorithm and try to do the analysis of that particular algorithm. So we will try to look all these things in our next section. Right? So try to practice properly the same problem, try to do it one time, try to do it 2 times, so that in the next section we will take another example and we will try to solve the example, right? So thanks for watching, and if you have got any doubts, you feel free to drop the queries in the Google Classroom. So thank you very much.